We're going to be looking at limits now. You've seen one limit, the definition of derivative. The limit as h approaches 0 of f of x plus h minus f of x divided by h. That's not exactly what we're looking at here now, so don't worry about that. We're looking at limits in general, and then specifically the limit as x approaches a number c. So x approaches 2 or x approaches -1. And this just is going to talk a little bit about numbers and the notation that we'll use. So let's look at a string of x values and see if we can decide if x is approaching a particular number. Say we have x equal to 0, 2, 4, 6, 7, 7.5, 7.75, 7.875. So I have a list of values for x. Now, thinking a little bit about those h values that we used when we were talking about limits, h approaching 0, h being the distance between x's. Well, let's see what h's might be here as we move in this direction for our h's, for our x's. So, if I think that if I follow the way the numbers are going, when I get to 7, then I go 7, 7.5, 7.75, 7.875. I'm still 7 point something, but I haven't hit 8 yet. So my guess is that x is approaching 8. And if I say x is approaching 8, let's look and see what the h value would be, the difference here. Now, these numbers are less than 8. So when I'm approaching 8, I'm approaching from the numbers that are less than 8. And so my first h value, if I'm at 0, would be -8, because then I have x plus h gives me what I'm approaching, 8. And then for 2, it would be -6, and then -4, -2. These are the differences. H is the difference between x and the number we're approaching, our c value. After -2 at 7, it would be -1, -0.5, -0.25, -0.125, which gets me to my 7.875, and I could keep taking half. 4, half of that was 2, half of that was 1, half of 1 is a half, half of 0.5 is 0.25, and so on. So each time I'm taking half the distance away from 8. So that x is approaching 8 with values that are less than 8. So I would really say that x is approaching 8 from the left, which are numbers that are less than 8, because if you think of it on a number line, in math we read the number line left to right, so I have negative numbers, I hit 0, I have positive numbers, and if I'm approaching 8 from the left, those numbers are smaller than 8. So that's the way this is set up, and I can actually write this in a shorter form. X is approaching 8 on the left. Now this is not a negative sign. That means from numbers that are less than 8 on the left side of 8. This is just the symbol that we use. Now, let's think about how close we were getting. I got as close as 0.125 away from 8. Could I get closer? If we switch to other decimals, I could look at 7.9, 7.99, 7.999, so that I'm getting closer and closer and closer to 8, and we say that I'm getting infinitely close. And so that's what we think of as our limit. X is getting infinitely close to 8. So now let's stop and look at an example, a data table with x's and y's, and we'll see if we can determine what x is approaching and then also what y is approaching. So here we have a table of function values of the function based on z. we have z equal to 10.232, 10.23002, 10.23002, 10.23002, and we want to try to put this table information in limit form using the limit notation. So when you look at the values for z, we keep saying 10.23, and then after that it's a 2, then an O2, then an 002, then an 002, but the 10.23 stays the same, and the digits after that are getting smaller and smaller and smaller. So we could say that z is approaching 10.23 because the other numbers are the tiny little numbers where we're getting infinitely close to just being 10.230. The p-values depend on z. So my values for p, see what they're approaching. 21.474, 21.4704, 21.47004, 21.47004. So here again it looks like my first two decimal places, along with the 21, are the only parts that are constant, and the rest after that are the numbers that are getting infinitely close to 0, so that my p-values are approaching 21.47. Now it says they're approaching. It never says it's going to actually equal that. And it doesn't say that z is going to equal 10.23. It says z is approaching this number and p is approaching this number. So we can write that as a limit. I can say the limit as z approaches 10.23 of my function p of z is equal to 21.47. But actually, I don't know that z is approaching 10.23. I know it's approaching 10.23 from numbers that are a little bit bigger than 10.23. If you think about these numbers on the number line, here is my number 10.23, and over here is 10.2302. Remember, we read left to right? So these numbers are on the right-hand side, and what we're doing, we are taking numbers over here approaching 10.23. Since they're on the right-hand side, they're numbers greater than 10.23. So this is actually the limit as z approaches 10.23 from the right-hand side. From the right side. So this is what we know exactly about our limit. Z is approaching 10.23 on the right. The values for the function are approaching 21.47. So this answer is actually what the function values are doing. Now let's think about this. We don't see anything on the left over here, but they could be there. We don't know that they're not there. We just don't see those numbers. So it could be that we have the limit as z approaches 10.23 of p of z equal to 21.74. That could be true. We can't see the left-hand side. We can't say we know the limit as z approaches 10.23 on the left. We don't know that, but it could be true. So we can say that we could have that limit right there. This is one of those parts that's really confusing, and you just have to practice a lot until you understand that we definitely have the right-hand side, but we could possibly also have it true that it approaches it from both sides, but we're not sure about that. Right? We want to look at the limit at a point when we have formulas to work with. When we did notation, we looked at tables that were already formed, so we saw how to do a limit if you look at the table. Let's see a particular function and see what happens with this one. Limit as x approaches 3 of negative 2x plus 10. Now notice that negative 2x plus 10 is a linear function. Remember, y equals mx plus b. So the graph would be a straight line. It doesn't have anything odd about it, no breaks, no jumps, not even any curves. So let's see what happens as we approach 3. If we want x to approach 3, what we have to do is approach 3 on both sides to see exactly what happens around 3. So if I pick, say, 2.99 and 3.01, if I plug in 2.99, multiply by negative 2, add 10, I get 4.02. So my x's are on either side of 3, but very close. And my y values, this one is 4.02. If I plug in 3.01, multiply by negative 2, add 10, the y value that I get is 3.98. Let's get a little bit closer just to see if we're kind of thinking about the right thing here. Let's try 2.999. If you plug that in, we get 4.002. If I get still closer on this side, 3.001, I'll plug it in, I end up with 3.998. So I'm moving, I was 0.01 units away, then 0.001 units away on the left. On the right, the same distance I was coming in. And it looks like when x is approaching 3, this looks like y is approaching 4. I've got a little bit bigger than 4 here, a little bit less than 4 here, but that leads me to think that the limit as x approaches 3 of this function is equal to 4. Now let's think a little bit further. What happens if we let x equal 3? Remember, this is a straight line. It doesn't have anything you cannot plug in. X could be anything. Negative 2 times 3 is negative 6, plus 10 equals 4. We actually get the same thing from that table that we get if we simply plug in, substitute x equal to 3. And so a lot of times that's step 1. Substitute whatever x equal to c is into the function. And many times that does give you the limit that you're looking for. That's how you get a y value. And the limit that we're looking for is a y value. So that's always going to be our first step. Let's look at another example. The limit as x approaches 3 of negative e to the negative 6 over x plus 1. Okay, a little more complicated than a straight line function, but the first thing we're going to do is plug x equal to 3 in for x. So if we do that, I have negative e to the negative 6 over 3 plus 1 is 4. 3 plus 1 is 4. E to the negative 6/4. If you wanted to do this on a calculator, be sure to do the exponent first. 6/4, make it negative. Then do the e to the x, and then make that negative. And if you do that, you get a number, and that number is negative 0.223. If you decide to use Excel to do this, one thing to remember in Excel, a leading negative here, you would have to write this as negative 1 times. And this is EXP of negative 6. In this case, we'll just do negative 6/4. But you could set it up as a function and put in various values on either side of 3 to see if you can get a table that approaches negative 0.223, and it would happen. But this time, it did work exactly to just substitute in. So we don't have to test a table. Substituted it in, and it worked. Let's look at another one. Limit as x approaches 1 of -3 natural log of x over x minus 3. This is a little more complicated function too. If I plug in 1 for x, I'll get -3 natural log absolute value of 1 over 1 minus 3 is -2. The natural log of -1/2. You could do that on a calculator and make it a little bit simpler if you rewrote that as -3 natural log of 0.5. Think about that. -1/2 is -0.5. This says take the absolute value of it, so I put 0.5. Sometimes you can do a little bit of thinking before you start using a calculator, and it means you'll punch fewer buttons and have fewer mistakes. Now, as it turns out, if you take this value, you'll get 2.08. Now, that's funny. Look, this started off with -3 times that. -3 times that. But the natural log of numbers that are fractions between 0 and 1 are negative numbers. So if I take ln of 0.5, I'll get a negative. Multiply by -3, I get a positive. So this also worked if I plug in my x value into the limit, figure it out, and I have a y value that exactly matches what a data table would do. Again, you could try this in Excel to create a data table approaching your number. Keep in mind, though, in general, when you approach the number, you don't actually use the number. But when we're plugging in here, that's one of the things that we do. Now, after this, we're going to look at a little bit more complicated function. This limit problem asks us to find the limit as x approaches -1 on the right-hand side. But we want to always plug in first, substitute in just x equals -1, and we can do that also if it's just from the right or from the left. So let's try that first. If I plug -1 in for x, -1 to the third is -1, times 2 gives me -2, plus -1 squared is 1, times 3 is 3, plus, and x is -1, over -1 squared is 1, minus 1. Now this is a problem. First of all, we have 0 in the bottom, but we also, -2 plus 3 is 1 minus 1, have 0 on top. That's not a form we can work with. You know that you can sometimes have trouble with zeros in the denominator, but this also has a 0 in the numerator that's actually going to give us better information. So since we can't plug in here, let's set up a data table. So we're interested in values to the right-hand side of -1, so that's towards 0. So let's pick some x's, say -0.99 and -0.999, and see what we get. If I plug this in a calculator or in Excel, remember in Excel you'd only have to put your function in one time and put your x values in, drag your formula. So the y values that I will get if I plug in 0.99, -0.488, -0.498. Well, if I just look at those values, my x here is approaching -1, and it looks like y is approaching -0.5. So it looks to me like the limit as x approaches -1 on the right is equal to -0.5. Well, how about if we try it on the left? Let's just try the left side. Let's approach this on the left and see what we get for our limit. So let me write over here, x, this side, where x is greater than -1, and we were doing x approaching -1 on the right. Over here, let's do x is less than -1, so we're approaching -1 on the left. So my x's here, think of the number line, -1 to the left would be -1.01 and -1.001. And my y values, if I plug in -1.01, I get -0.513. Now it may seem a little bit odd to get different numbers, not the same distance away, but this is not a straight line. So the y values are not going to be the same distance away when the x values are the same distance on either side. And if I plug in down here, -1.001 for every x gives me -0.501. Well, here again, our x's were getting closer and closer to -1. -1. And the y values still look like they're getting close to -0.5. So if I have the limit as x approaches -1 on the left, I get the same number. Now what that tells me is that if x approaches -1, the limit is -0.5. If you get the same thing from both sides, that's what the limit is equal to. Now we found out we could not just plug in -1. That doesn't matter. This does not say x equals -1, what does y equal? This says find the limit as x approaches -1. Get infinitely close to -1. What does y get very close to? And y gets very close to -0.5. Now, do you have to always do a table? No, you don't have to always do a table. That will work. It always works, but sometimes there are other ways that may be just as easy. Let's go back and see what happens if I factor this. In the numerator, I can factor out an x. 2x squared plus 3x plus 1. So I pulled an x out of each term, lowers my exponent for each one. In the denominator, x minus 1 times x plus 1 gives me x squared minus 1. Well, let's go a little bit further. This is a quadratic, so you should be able to factor that, but let's think about something else. As x approaches -1, remember when I plugged in and I got a 0 on top and a 0 on the bottom? If I plug -1 in here, x minus 1, -1 minus 1 is -2. That's not a 0. But if I plug -1 in here, this gave me a 0 on the bottom. That means that factor should also be in the numerator because I got a 0 in the numerator. So now we need to factor on top. And one of my factors should be x plus 1. So let's see what the other might be. 2x squared was 2x times x. A 1 here, the only way to multiply and get a 1 is if that's a 1, everything's positive. So that should be the other two factors on top. Times x minus 1 times x plus 1. And yes, I did indeed get an x plus 1 top and bottom. So those factors cancel. And what I do next is sub in x equal to -1. Once I get to the part where I've gotten rid of the terms that gave me 0 top and bottom, then this fraction that remains should give me a limit. So my limit is going to be the same as if I just plug in -1 for x. -1 here, 2 times -1 plus 1, over negative 1 minus 1. So I have negative 1 times negative 2 plus 1 is another negative 1 over negative 2. My limit is 1 over negative 2 is a negative 1/2. Oh yeah, negative 0.5. So you can set up a data table, which looking at all this now and thinking you have to factor, you might find it easier to think, I'm just going to set up a data table, which is fine. But you can factor and cancel, and you will need to be doing factoring later in the course, so this is a good time to start getting some help with it. So we also have not just substitute in, we have a second thing, we can do data tables, and now we also have our third thing, we can factor and cancel. And that also helps us find a limit. In this section, we're going to look at the limit at a point on a graph. So I have a graph up here. I have some holes in the graph. Got a space between here. So let's first look at the limit as x approaches 1 on the right of f of x. Now when you're talking about x approaching 1 on the right when you're on a graph, here's 1, here's the right side of 1. You don't go all the way over to 2. Remember, limits are very close to a point, infinitely close. So you just move a little bit to the right of 1 and go back towards 1. And then you go to the graph about the same place and go towards the same direction, towards 1, and you find out what the y value is, because the limit is the y value. So when x is approaching 1 on the right here, it looks like the y value is 2. So that would be the limit. There's a hole in the graph, but that doesn't matter. We're approaching that value, and so it looks like we're approaching 2. Maybe a little bit less than 2, but I'm going to call it 2 for here. Well, how about the limit as x approaches 1 on the left? Well, we do the same thing. We go to 1. We go to the left of 1 a little bit and then go back towards 1. So if I go towards x equal to 1 this way, I go up to the function and I go towards that point. And that's supposed to look like that's about y equal to 1. So the y value is the limit. So as x approaches 1 on the left, y is approaching 1. And here I actually have a dot there. It's filled in. It includes this point, and it does not include this point. That makes this a function. Remember, we're dealing with functions, and I can't have 2 points above each other. Vertical line test. So my 2 limits are different. Does that tell me something about the limit as x approaches 1 of the function? Well, when you do data tables, you find out if you're not approaching the same thing, you can't just write the limit, and it's the same thing here. Since my limits are different, the limit as x approaches 1 of f of x, we say does not exist because the sides are different. Now, when I wrote this x approaching 1 on the left, I said I had the point right there. So if I want to plug 1 into my formula, that would actually be the value f of 1, because the point is there. If I plug in x equal to 2, I'll get some number up here, maybe 1 2/3. So when I plug in 1 into my function, I get this point. When I plug in 1, I don't get the point up here. So this 2, that is not f of 1. It's different. Well, let's move away from 1 and let's look at another point. How about we go over here at 3? What is the limit as x approaches 3 of f of x? Well, if x is approaching 3, If I go up here a little bit and down, looks like I'm getting close to 0 on the left side. If I go on the right, I'm down here, and I go back up to where x is 3, and it still looks like y is equal to 0. So we think about it the same way. A little bit on one side, and we see the y's. A little bit on the other side, and we see the y's, and we're approaching y equal to 0. So that's the limit. Let's jump over here to where this hole is. This is, looks like, well, I'll say -1. So let's look at the limit as x approaches -1. We do the same thing, both sides. I'm on the right-hand side of -1. I go up to the function, and I'm going in that direction. And on the right-hand side, it looks like I'm getting close to y equal to 3. On the left side, I go up to the function up here, and I'm going towards, in the same direction, towards the right, x equal to 1, and it still looks like 3. So my limit as x approaches -1 is equal to 3. Again, it doesn't matter what happens when x equals -1. It's just that as x is approaching -1 here, y is approaching 3. Now, I do have a value for f of -1. F of -1 is equal to 4. And that has absolutely nothing to do with the limit as x approaches -1. So we can have a value that's equal to the point there, like we did over here, like we did here at 3, or we don't have to. We just need to know what y is approaching as x approaches a particular number. We're going to look at limits now that involve infinity. And that means that a couple of places where we have numbers, for example, the c, we could have infinity or -infinity. And or where we have L, we could have infinity or -infinity. Now, the infinities are just really large numbers, very, very large numbers. And since x would be approaching infinity, or L would be approaching infinity, you don't have a particular number. You just have to try and get bigger numbers, or you end up with numbers that continually increase or decrease for the negatives. So let's look at a function and try to find the limit as x approaches -1 of -2 natural log of x over x plus 1. Now, we actually did one very similar to this a little bit earlier in a video on limits. Let's see what happens. First step always, plug in your value for x. If I substitute in here, what I get is -2 natural log of -1 over 0. Can't have 0 in the denominator. If I take the absolute value of that, I would have -2 natural log of 1 over 0. Well, that didn't help. This is not the 0 over 0 that we have alternate things we can do with, but we can always set up a data table. So let's plug in some numbers as x gets very close to -1 and see if we can find some values. So if I'm thinking of -1, that's between -2 and 0. So if I'm approaching -1, let's put in for x -1.01, -1.001. Cannot put in -1. I don't get anything I can use. So let's go to the other side of -1 at -0.999, -0.99. If I plug in -1.01 in here, take the absolute value of it, take the natural log of it, multiply by -2, what I end up with is -9.23. Okay. If I plug in -1.001 over that plus 1, take the natural log, multiply by -2, I'll come up with negative 13.81. That's a big change. We're not approaching anything, it looks like. So we go to the other side. If I start away from negative 1, negative 0.99, I get negative 9.19. Similar but different from being 1/100th of a unit on the other side. And if I put in negative 0.999, I actually get, if I round to 2 decimal places, the same thing. But I suspect that beyond these 2 decimal places, I do have different numbers. And I'm guessing that if I plug in something with an extra 0 here and another 9 over here, I'm going to get even bigger numbers. These are not approaching any particular number. They're just getting bigger. They're increasing. And so the y values appear to be getting larger and larger and larger. So I am guessing, estimating, that I can just plug in negative infinity to represent what is happening. So I can write this limit up here, the limit as x approaches negative 1 of negative 2 natural log of x over x plus 1. I'm going to say that equals negative infinity. That's all the information I have. X approached a number. I did it on both sides because this didn't tell me right or left. And that's the number, the result that I got. No particular number, just getting bigger and bigger. Let's think about that a minute on a graph. Here's negative 1. Now, I have here at negative 0.99, which is on this side, I'm at negative 9. I might as well call that negative 9 right here. And when I got a little bit closer, I was at negative 13. So my numbers here are going down. And the same thing happened that I erased on the other side. I was also at about negative 9 and then about negative 13, so the numbers are going down like that. So what is happening is I'm getting larger and larger and larger, but since I know I can never have a negative 1, what I have here is a vertical asymptote. And the definition of vertical asymptote looks a lot like the way we wrote this limit problem. The definition of a vertical asymptote at x equal to c is the limit as x approaches c of f of x, and it can equal either positive infinity or negative infinity. And that means at that point, whatever that c value is, I have a vertical asymptote. So that pretty much takes care of what happens if our infinity part goes with the L. The limit is infinity or negative infinity in this case, and so that tells me I have a vertical asymptote. So let's think about what happens when x is approaching positive infinity or negative infinity, about that part. Now let's look at a function that you've used before. It's the logistic function. Now we have a logistic function, m of t equal to 500 over 1 plus 165.67 e to the negative 0.06t. That is a logistic model. When we looked at logistic models earlier, we found that they're sort of S-shaped curves that level off. And when they level off at what is a horizontal asymptote. And what I can do here is plug in values where t is getting larger and larger and see what I get for m of t. You should already know that because, remember this 500? That's the maximum value we can have. This is 500. So as the t values get very large, if I take the limit as t approaches positive infinity of my function m of t, I will get 500. This is previous knowledge. We've already looked at this and we know that this is true. And this is what gives us our definition for horizontal asymptote. It's a horizontal asymptote. We have the limit as x, or whatever your variable is, approaches either positive infinity or negative infinity of the function, and it equals a number. And if that is the case, the horizontal asymptote is y equal to L. That's the number for the horizontal asymptote. So let's look at another example. This is one you already know. I didn't set up a data table because the logistic function means this maximum of 500 is the value for the horizontal asymptote. Limit as x approaches infinity of 3x to the 7th plus 4x squared plus 6 over negative x cubed plus x plus 2. Now, what do you do with one like this? Well, if x is approaching infinity, we'd have to pick large numbers. We would have to let x equal 100 or 500 or 1,000, getting very large. Or you might start off with 50, 75, 100, just to see if that gives you some information. But with something like this, trying to plug it into a calculator or anything that gives you numbers, that can be really messy. So there is actually a better way to do this. And what we can use are called dominant terms. So let's look at what the definition is for dominant terms. So the dominant terms, you saw in the definition, are the terms that have the highest power in the numerator and in the denominator. So for this function, the highest power is x to the 7th. And in the denominator, it's negative x cubed. Now, it doesn't matter if it's a positive or a negative, if it's an even power or an odd power. If I put in 100, raise it to the 7th power, that is huge, even compared to 100 squared, and certainly bigger than 6. And the same thing down here. So what we do is we say that to do our limit, this limit is going to be the same as the limit as x approaches infinity of 3x to the 7th over negative x cubed. Well, I can reduce the x's, and I'd have 3x to the 4th, and it's negative. And if I put in very, very large positive numbers for x, I put in 100, I raise it to the 4th power, it's just huge. It gets bigger and bigger and bigger. So this limit is actually negative 3 times a huge positive number is negative infinity. So this is a problem where not only did x approach infinity, but our limit also turns out to be infinity. Here's another example when x is approaching infinity. Since I have negative 5x squared minus 7 over x squared plus 2x minus 24, when I'm approaching infinity, I can use dominant terms, so that the term that dominates the numerator is negative 5x squared. It's the term with the highest power. The term that dominates the denominator is x squared. If I'm plugging in a very, very, very large number, the negative 7 on top and the 2x minus 24 on the bottom really have no bearing on the numbers that I get. So this limit is equal to x approaches infinity of negative 5x squared over x squared. Now remember, it's not that the two functions are equal, it's end behavior. In the long run, as x approaches infinity way out on the x-axis, these have the same limit. Here I have x squared over x squared. That is equal to -5, and that is my limit. Now, if you think for a minute back about our definition for a horizontal asymptote, if x is approaching plus or minus infinity and you get a number, that number is y equal to the horizontal asymptote. So what we have here is y equal to -5 is the horizontal asymptote for that function. In the long run, it levels off to -5. If our answer had been infinity, like the previous example, that means in the long run it just keeps getting bigger. Or if it's negative infinity, it keeps getting smaller. But this does go back to tell us not only is that a limit, but for this function, that will be the horizontal asymptote. Let's look at a couple more of these examples. Limit as x approaches negative infinity of 6x plus 3 over x squared minus 9. X is approaching infinity. I need to look at the dominant terms. Note this, dominant terms are used when x approaches plus or minus infinity, not when x is approaching a number c. My dominant terms here are the 6x over the x squared. So we look at the limit as x approaches negative infinity of 6x over x squared. And this time, when I cancel the x and one of the x's in the bottom, I get the limit as x approaches negative infinity of 6 over x. I don't just get a number. So I have to think now, well, what do I do as x approaches negative infinity? Well, let's put in some numbers. I'll have 6 over negative 100. Well, if you think of that as a decimal, that's negative 0.06. How about 6 over 1,000 or 10,000? That would be negative 0.0006, tens, hundreds, thousands, 10,000s. As my denominator, as my x's are getting bigger, my fraction, my y's are getting smaller. The limit here is 0. So I use dominant terms and I got a 0. Well, 0 is a perfectly good number. That just tells us that y equal to 0 is a horizontal asymptote for that function. It doesn't mean the limit does not exist. It means the limit is 0. Remember, the limit is what y is equal to. Let's look at one more. Limit as x approaches negative infinity of 5 to the 2x power minus 9. Well, I can't use dominant terms because I don't have a polynomial in the numerator and a polynomial in the denominator, so I don't have powers of x. So about the only thing I can do here is substitute in numbers similar to the way we had to substitute in the last example. I want negative infinity. So let's think about what might happen. Say I have 5 to the 2 times negative 100. 5 to the negative 100 minus 9. When I think negative exponents, I like to make them positive by putting them in the denominator. 1 over 5 to the 200th. Well, 1/5 is 0.2. That's already a decimal. The bigger the denominator gets, the smaller the fraction. Like in the previous one when we had 6 over 100 and 6 over 1,000 or negative. So this part right here is just going to 0 because if x is even larger negatively, 5 to 2,000 is even smaller. So this whole thing is 0 minus 9. That limit is equal to negative 9. So this exponential function has a horizontal asymptote of y equal to negative 9. And if you think about exponential functions, they either increase or they decrease, and they do have horizontal asymptotes. So when you have a limit, there are lots of different possibilities. If you plug in numbers on both sides or you plug in infinities, you get a lot of different answers, and it just takes a lot of practice to figure out how to do the problems.